Great. Guilhem, you ready?
I'm ready. Let me actually put
Okay.
my video on for a second.
And I will introduce you. Guilhem is Chief Architect at the BM team, building decisioning technology. And since 2020, he leads the architecture of the next generation of decisioning platform at IBM. And he was deeply involved in the navigation system that now famously known as the Mayflower Autonomous Ship. And that would be a major topic of his presentation. And I specifically asked Guilhem to tell us not only what it does, it's quite impressive, but it's very interesting for this more technical audience to know how it's done. So,
Thank you, Jacob.
Also your co-presenter is Dan Scott, who is Chief Technical Officer at Marine AI, right? Okay, go ahead.
Yeah, thank you, Jacob, for the introduction. So Don was supposed to be with me. So first of all, I want to say hi on the camera, and then I'm going to bring you here. I want to preserve the bandwidth for the voice, right? So I hope you won't mind too much. Besides the camera inlay, the overlay of the camera gets in the middle of the slide. So I'll leave it this way. I'll put the camera again on for the question and answer at the end. Don Scott is the CTO of Marine AI, who is part of this endeavor, and he had the last minute issue that prevented him to join me and take part in this talk. So I'm going to be the only one presenting. I hope you don't mind. This is going to be recorded, so we'll have an opportunity to watch, and he's also on the Slack channel. So if you have questions that I don't know how to answer, I will defer to him to answer them asynchronously when he can. Anyway, let's get started. The Mayflower Autonomous Ship, which you see on this picture here, taken at the dawn of the day, what is it? Who made it? What are we talking about here? So it will be a talk that is a little bit of a change from pure technology decision talk that we have had in the last few days. So we will have an opportunity to explore another area, but there is a link to decisions. There is a link to rules that I will present later on. So who made this boat? So this boat has been built by MSAB. MSAB is a company that builds underwater equipment, has been doing so for the last 20 some years for various industries, including defense, as you can guess. The people who are building the submarines are very experienced in the actual hardware, propulsion, etc., and wanted to explore a new area for the next 400 years. So 400 years ago, in 1620, the Mayflower ship departed from Plymouth, UK, and brought a pilgrim to Plymouth, US, in Massachusetts, close to Cape Cod, on a 3-month-long journey that was obviously quite dangerous. In order to celebrate this, the CEO and also the visionary, Brett Fan, the president of the MSAB and Submergence Group companies, the MSAB is part of the group, has decided that it will build a ship that, instead of being a mimic of the past, will be looking toward the future, and consequently, that ship will have to be futuristic and completely autonomous. So MSAB was in charge of all the technology. I was about to say the hardware in IT world. And then a company was created especially for the purpose of this software part called Marine AI, whose purpose was to build a software that would steer the ship in an autonomous fashion. So the ship was given 2 missions. First mission is cross the Atlantic, carrying over scientific payload to carry on scientific experiment in the middle of nowhere. And the second goal is to prove that we can have the right technology to build a ship that can drive itself. So I put a picture here of the ship on purpose because you can see the three hatches. I'll show you in the next slide. I'll show you another angle of the ship, but you can see the three hatches that are used to lower equipment within the hull of the ship. I didn't mention, but the ship is 15 meters long. That's 45 feet in the US, 6 meter wide. So that's a beam of 18 feet. So it's not that big of a ship, especially when you're facing the waves in the Atlantic. They can be as big as high as a ship is long, right? So it's basically the minimum size to be able to cross the Atlantic and survive that, right? Cross the Atlantic safely. And as you can see, the shape of the ship has been, so the hull has been custom made, and the shape of the ship has been defined as a trimaran. And there are a couple of reasons for that. First reason is that it is a profile that gives less drag in the water, stability, which is quite important, and also gives more surface area. For what's quite important is that the ship is powered. It's covered with solar panel. It has batteries inside. The solar panels are recharging the batteries, obviously, during the day, but the ship is designed to work 24/7, and at night it's drawing power from the batteries. Now, if the sky becomes too cloudy, or for some reason the solar panel charge is not sufficient for the electric equipment on board, there is a generator on board, a biodiesel generator encased in the hull that can be started automatically if the voltage of the battery drops below a certain threshold to avoid depleting them completely. So this is a ship. The other thing you can see on that picture, and that's part of the reason why I put it here, is that there is absolutely no space for human being on board. There is no living quarter. There's no galley, which is fancy marine word for kitchen. There is no cabin, which is just a fancy marine word for bedroom. There's no place for crew to actually be on board, live on board. There is no potable water, drinkable water on board. There is no bathroom. There's nothing, right? Obviously, this is saving a lot of weight. This is also saving a lot if you think about some of the potential mission that such a ship could accomplish, scientific expedition. It is a saving as compared to a regular oceanographical vessel. So if you look at the ship sideways, you see a little bit what's inside. So what's inside is obviously engine, which is an electrical engine, batteries to power this engine, but to power other things as well on board, backup generator, which I just mentioned, and then a series of IT systems that some of them are running rules, and that's a link with this talk. In the middle, there's a payload bay that basically can take in 700 to 800 kilograms, so that's about 1,500 pounds of scientific equipment, and that is used to conduct scientific experiment. I'm going to come to that in a slide or two. One other thing that we are going to be very interested in for today is a navigation system. So there is one of the cabinet here pointed by the arrow that is including the system that are used to navigate the ship across the Atlantic. This has about the size of a carry-on luggage, and the software that's on board drives the ship all the way across. Okay. Now, if you look at the cross-section of the ship, you will see that there are three consumers that are able to draw power from the battery and the generator system. And they are obviously the engine or the propulsion system. So the engine driving the propeller, but also the hydraulic pump for the rudder control. There's a little bit of, the usual ship mechanics that you'll have on any regular ship. The second thing that consumes power, that draws power, is the navigation system, which obviously is a set of computers, so they do require power. And then the third piece is the scientific equipment. So every day the solar panels are producing a certain number of watts of energy, and that is spread across the three main consumers. Obviously, you can think that there is a priority. Navigation system need to be up at all time. If there is not enough use to power the scientific equipment, well, their power is going to be cut, and that's it, right? If we cannot carry on a scientific experiment, it's not that big of a deal. But we want to be able to always be in control of the ship, that the ship can navigate and take the right decisions to know where to go. All right, so I mentioned two main goals, so science and navigation. For science, so I should have mentioned that earlier, but obviously this achievement of building such a ship and having it cross over the Atlantic is not done by just one company. It's a group of partners and contributing companies, organization that have been able to pull this off together and build up the whole and behaviors, the whole experience. Among other things, we have a bunch of scientific experiment on board, at least on that first crossing, because obviously the payload can be changed over time. But for that first crossing of the Atlantic, we had those. So I realized my first one is actually not showing up. It turned out black on black, but we have experiments to analyze water, especially some elements in the water, some elements that are causing pollution of the water. So we do sample that. There's some chemistry to detect some level of acidity and these kind of things. Experiment on the sea level, that is actually quite important because it's what's driving our climate. So we do have experiments on board for sea level. There's one that's not mentioned here. It's a microplastic. We also measure the quantity of microplastic at different points during the journey. Whale songs. So I should mention this. We have the capability on the ship to actually suck in water from outside. So there's basically a through hull intake that allows to suck in water and analyze it, and then either for some experiment we analyze on the fly and save the data, or for some other experiment like we just actually take in a little bit of water and drop it into kind of a plastic bag. You know, those bags that are used for freezing in a freezer at home when you have leftover food. Same type of bags, right? Where we put a little bit of water sample from various places. So there's a machine that is able to fill them and label them and put them aside so that once the journey is over, we can go ahead and analyze them. We also have an experiment that we call the electronic tongue, which has been actually developed by the IBM lab in Zurich, Switzerland, which is sampling various chemicals on the water. And then we also have hydrophones. So we have hydrophones that are listening to sounds in the water. And we have a few scientific experiments also developed in contribution with IBM, where we do analyze the sound emitted or actually caught by those hydrophones, so emitted by mammals, to figure out if they are mammals and which one, what species, etc., to inventory various mammals, some dolphins, some whales, etc., to try to count them, try to know where they are, where they're moving. So there's this capability to conduct experiments that are also related to animals in the water. So that's one of the goals of the ship. This picture here is mentioning some of the sensors that have been included on board the ship. So the sampling system that I was mentioning, hydrophone, yeah, obviously I didn't mention, but temperature, etc. Right. So those are some of the things we have on board. Now the ship also is equipped with cameras and accelerometers and radars, etc. All the sensors that are useful not just for the science but also for the actual navigation. So I'm going to come to that. Now let's remove our science hat and put our IT hat for a second. The ship is considered to be an age agent. That is, if you look at an age architecture, we have three main pieces. We have the edge device itself. So the ship is one such device. Then we have the cloud. And then we have the ship control center, which is in UK. So in the ship control center, we can actually compute where we want to go. We can build up models. And I mean by that, ML models, decision models, etc. We'll come to that in a few. And then all of that is posted on the cloud, where it can be sent over to the ship. We have also other components on the cloud. We have components for a public portal. I think I have the link at the end of this deck. The portal is called MASS 400, MASS for Mayflower Autonomous Ship 400 for the anniversary of the actual Mayflower. So mass400.com, where you can actually see where the ship is, track it, see where it's going, see the level of energy that's left on board, and what speed it's cruising at, etc. And then we also have a portal for the scientific teams. So the way it works, it's the same way as the International Space Station. That is, the ship is available for scientific teams who want to build up an experiment and have the experiment be installed on board. So they can provide the primary foundation operating the ship with the scientific equipment. And they will get the result at the end of the mission. Consequently, they need a portal to go and access. They can access some data during the journey, and then the rest of the data once the ship has landed. So we have those pieces, right? The control center, the components on the cloud for access by the scientific team and by the general public. And then we have a link to the ship itself, which contains obviously encrypted comms. So it is quite important that the ship is secure and cannot be hacked into, but also the navigation system and the scientific experiment. There's a link between scientific experiment and navigation system because one of the things we want to be able to do is that a scientific experiment can influence the navigation. For example, if a science experiment determines that this sound over there coming from the port side, 3 miles or 10 miles down, may be mammals that need to be investigated, that it's smart to inform the navigation of that and change course and decide to go and explore this to maybe get a better sound quality and acquire a better sound sample and conduct further analysis. So it's important that this link exists. And finally, the most important piece of this diagram is a link in the middle that is a dashed line written intermittent. I don't know if you guys can see my mouse here when I move it, if it's coming across, but basically this is the most important piece. The ship is linked to the shore through a sat link, which is just a regular satellite link that you can get on any ship, which is both very expensive and very slow and not that reliable. That is why it's a dashed line. So the way we build it is that should communication be available, the ship can actually talk to the cloud and maybe download updated models. But should communication not be available, the ship can actually steer by itself. We have built this in such a way that the ship is not reliant on being on the cloud, right? And if you think about it, we are seeing more and more cars on the market that want to drive themselves, right? This is Jacob's point that he said earlier, yesterday, I think, that in 20 years from now, our kids are going to look at us saying, what, you actually drove those cars? Probably this is going to be the question that they ask us. Well, today, the autonomous vehicle market is barely emerging, but you wouldn't want your car to just not know to stop at a red light or anything like that because it will display a network error. I couldn't contact the cloud server to tell me what to do, right? You want some level of autonomy to be part of the vehicle itself and not reliant on some external network that may or may not be available. If I remember well, the bandwidth of the sat link is like 356K, which is just nothing. Knowing that we want to use it to, first of all, to track the ship right? Make sure that it can send its position, but also send a few pictures. So if you go to the Mass400 portal, .com portal, you will see that there is a section in the dashboard section. There's a section at the bottom that shows views from the ship. It may be connected or disconnected depending on the time. If people on board the ship tinkering with equipment, they will disconnect this to make sure they don't trip the power. Last time I checked a couple of days ago, it was connected. The ship is on a yard, and you could see the view from the yard. So the ship has cameras on that arch structure that you see on top of it. If I go back here to this picture, you can see here on the top on the radar arch, there is a regular radar, but also a few cameras that are facing forward and backwards, looking front and back. Those cameras, in addition to be used as an input for the ship navigation system to compute what's around it, they are also fed through the stream, compressed and sent over on the satellite link, so that the general public can have an idea of what the ship is doing. So that's basically the general picture of the component of the system. On the ship, we have the software to sense what's around, compute, and decide where to go, plus a scientific payload. On the cloud, we have all the management of the edge device, plus the portal for the general public and the science. And in the development center, we have the location where we craft those models. We have mission control, where we can actually interrupt the ship and give it new orders, or take the control remotely in case something bad happens. And we also have the weather data that is supplied by the weather company. Now, what are some of the challenges that the ship needs to face? First of all, we have regular Rotary Challenges, right? Those of you who have their boat driving license, who took the test, may remember those pictures here with the rules of the road. So at sea, there are rules as well. Those rules are actually fairly ambiguous. They don't tell you everything. They tell you what you need to do in some cases, but there are cases where it's not clear what to do. So those are the colregs, collision regulation. And then we also have the SOLAS rules, the safety of life at sea, SOLAS, which are rules related to rescuing other people and making sure you don't put anybody in danger. Obviously, you cannot put a ship and have it registered and put it at sea where it could cause a danger to others, including to human life, without being able to prove that it does respect the regulation, right? That is an absolutely necessity. The other challenge is obviously to be able to explain those decisions. Think about if you are an insurance company and somebody walks to you and say, "Hey, I want you to insure my ship, but there will be nobody on board." You would seriously want that person to be able to explain why the ship is taking those decisions. Security, and then management without or with limited or without connectivity. So those are some of the challenges that need to be solved. And remember that when the ship is in the middle of the Atlantic, if all of a sudden we lose comm with the ship, we don't know where it's at, it may take 8 to 10 days just to get at it. So it's not like a lab experiment where if your computer, for whatever reason crashes, you just, a robot experiment or what, you can just pick it up. Once you've sent it, you just have to make sure that it works. It's not easy to go back to it and hit the manual, kill switch and say, "Hey, go back home," right? I like to think about the decision that the ship is taking as a hierarchy, kind of the Maslow pyramid of needs for, the human needs about security, physical safety, being fed, being heated, etc., all the way up to social acceptance and a sense of meaning of life and all of these things, the typical pyramid. Well, it's kind of the same thing for a ship, right? There are some basic needs that the ship needs to satisfy, and for that, for which it needs to take the right decision just to survive. For example, such a ship, or any ship actually at sea, if you stop the power to the engine and wait, the ship is going to turn sideways to the waves. That is just the way of physics works. And when the ship is getting the waves beamwise instead of from the front, it exposes a much shorter length of hull to the waves in a direction that was not really designed for that. And it ends up being rolled more easily. And the risk is obviously that the ship is completely rolled over and capsized. To avoid that, you basically, in the middle of the Atlantic, you never stop. You always maintain a little bit of speed just so that you can point your bow in the direction of the waves. And obviously, to do that, you need an operational system, right, including a propeller that works, that has not been entangled in a fisherman line or anything like that, and a navigation system that works and can take those decisions. And then you need enough juice in the battery that you can actually power all of that. And then you have higher decisions that have a higher degree of, in that hierarchy, manage local situation, avoid collision, right? And then you have higher order rules, such as following regulation. It's more important to maintain the ship alive and then to avoid collision than to actually follow the rules. It's important to follow the rules, but you have to break the rules to stay alive or avoid a collision. You would do so, right? And then you have more of the strategy goal to navigate towards your destination and collect the data that is needed for the science, etc. So on board the ship, we combine 3 types of technology, and I'm sure this is going to echo some of the presentation we've seen already in the past couple of days. We see that we saw the presentation from Gregor on Monday, but some others as well, where we see a mix of, decision-making is not just rules. Decision-making is often a combo of machine learning. In this case, we have machine learning, we have rules, and we have optimization. And those 3 components are used in conjunction. So in this case, machine learning has been used for the vision part, using an IBM protocol, Maximo Vision. So I should have mentioned this, by the way. I should have mentioned this early on. In this behavior, what IBM has done is to offer some technology to Marine AI. And Marine AI has taken this technology and built the system, trained the system, written the rules, written the optimization model, etc. So Marine AI is the IP owner and the company actually owning the smart software that powers this ship, which they call AI Captain. And IBM has been a provider of technology and hardware to run this, right? So it's not an IBM product, even though IBM actually advertises it because it's a showcase of the technology, but it's not an IBM product. It's a product for Marine AI. And that's why I really wanted to have Don on board. He couldn't make it, unfortunately, but it's his doing, basically. So the way it works is the following. On the left-hand side, we have sensors. There are 2 types of sensors on board the ship, sensors that are reliable or not reliable, or building structure or unstructured information. Cameras are giving unstructured information. We have cameras facing front and back of the ship, 2 of them each, and also sideways, and they take picture of what's around the ship. But the picture are really unstructured. So the first thing we want to do on those images is to apply a vision algorithm. So we have a ML model that has been trained with millions of images of everything you can see at sea. And that means tankers, sailboats, kayaks, swimmer, floating debris, birds on the water, floating container, island, whatever, right? Everything. You could not imagine how much stuff there could be on the water. Plus, obviously, all the things that the human put there to guide the navigation, like all the buoys and signals that are at sea specifically to be seen and to give indication to mariners. So cameras are giving that, and the ML vision that's been built for that purpose is actually helping to classify what's around the ship. Same thing with the radar, right? The radar has the added value to see at longer distance than the camera, but it's giving information that is that requires some interpretation to be more structured. And then we have information that is already structured, such as AIS. So AIS is automatic identification system. It's the same thing as the transponder for aircrafts, for example. It's a device that all ships, all commercial vessels, and all ship 25 meters and longer, so 75 feet and longer, need to have on board. It's mandatory by law. And that device sends over radio signals and also sometimes satellite link as information of which ship it is, where is it going, what speed is it at, what is the dimension of the ship, which is quite important actually. Some ships can be huge. It gives you also an idea of the maneuverability of the ship. And basically there is a record of information that is being sent by the IIS. Now, there are a lot of vessels at sea that do not send AIS information, because you would think, well, if I have precise identification lat long of the ship and destination and direction, why do I need to bother with cameras? Well, there are tons of vessels at sea that are not sending AIS signal. First of all of those that are not equipped, all vessels less than 25 meters, all the things that are just not vessels, for example, floating container, or some debris obviously are not sending their position, they are just hazard floating at sea. And you would be surprised, some studies are stating that there are 300 to 400 containers lost at sea every year. It's one a day. It's just crazy, the number of containers that are lost at sea. So some of them sink, but a lot of them keep floating around and present hazard for the navigation. If you go to marinetraffic.com, by the way, the same way as you can see all the aircraft flying over Earth at any point of time, you will see all the ships that are cruising at sea. And it's just, I mean, it's terrible the number of vessels that we have at sea at any point of time, night and day. It's really huge. Go check it. It's really worth it. But anyway, so some ships do send AIS information, in which case we have structured information. So the first step is to have a data fusion algorithm that is mixing this unstructured data with the structured data to kind of build a mental picture of the situation around Mayflower, what's around it, and try to build up speed vectors of those other objects, identify them and build speed vectors. The second step, which is where rules are being used, is so we use a rule engine to evaluate the situation ship by ship. For Mayflower and this obstacle, or Mayflower and this other, I was about to say target, right? Which is more of a military word, but you get the meaning that it's any other thing that's around me, whether it's moving or not moving, whether it's an island or a tanker or a kayak or whatever. So for Mayflower and each target, what are the routes that are legally possible, right? And in fact, in the rule engine, we put two things. We have two series of rules. We have a series of rules that are supposed to represent the law. For example, this ship has restricted maneuverability. Even though it's coming from my port side, I need to yield and let this ship go first. That other ship is a sailboat. It has right of way, so I need also, to slow down or avoid it. So those are the rules, right, of the law. But then there are the rules coming from seasoned mariners who know what to do. There are things that even though they are legal, you do not want to do. For example, if a fisherman vessel is coming from your starboard side, so it has right of way, you would slow down, let it pass first, but then you would not accelerate and ride just past that fishing vessel. You could do so behind the sailing vessel, but you would be crazy to do so behind a fisherman vessel, because it may be dragging lines, it may be dragging nets, anything that may be floating behind that vessel, in which would entangle your prop and obviously run in trouble. So there are, and then there are a lot of people who are simply not following the rules at sea. If you sail a little bit and you look at what's on the water, it's crazy the number of people who have just ignorance of the rule or that are completely careless about the rules. So it's not sufficient to just know the rules that are legal. It's also important to have a second rule set, which represents the knowledge of expert mariners of, in this situation, I don't want to do X, I prefer to do Y. So that gives a series of possible routes. But then we also have an optimization engine in the picture that is solving a couple of problems. It's solving the problem of among all of those routes, which one do I want to take based on optimization criteria. And by that, there are several optimization criteria that can be decided and that can be picked. There are criteria related to the shortest route, or the route that has less turn, or the route that will put my ship in front of the wave instead of sideways the most time, to avoid being banged over by big waves, these kind of things. Also, the weather is taken into account to avoid storms, but also to maximize exposure of the solar panel. So this is basically a constraint programming problem that is being solved by a solver. And the last point is the actual control, where we have the control of the ship, especially being able to go from a software issued command to drive all the robotics that are going to actually affect back on the world by changing the rudder position, the speed of the prop, etc. So all of this is done within the ship. And the link to the command center is used for obviously reporting position, but it's also used to upload newer models to the ship. So at the development center, we have this capability to build newer model, newer decision model, new optimization model, new ML models, and upload them to the cloud. And when the ship is in range, it can actually download those models and deploy them on the fly on the runtime that's on board the ship to now run with a new model. This has proven obviously useful during the development phase when models were being tested at sea, and it's a must-have capability to just refresh basically the software on board the ship. It's also a way to send weather information to the ship, maybe newer chart if needed, etc. All right, I had a slide here. I'm going to skip that one. It was more about what is a rule, what is a decision table. For this audience, I don't think it's needed. Optimization, I just mentioned that. The optimization process that is used to find the best route, you see it on the left, among possible routes, following channels, etc. So I'm going to skip that. I have one last slide here that I want to mention. So the way we build this is that we have a lot of capability on board the ship: mission control, vehicle control, autonomy management, when to kick off the generator, when to slow down. The ship is able to slow down to reduce power consumption if there's not enough energy left for cruising at the current speed. By the way, I didn't mention it, but the cruise speed of the ship, the average cruise speed is 5 to 6 knots. It can cruise at 7 to 8 knots, but that's less efficient from a power standpoint. 7 to 8 knots is about the cruise speed, the normal cruise speed for this for this length of hull. There is a physics law that says that based on the length of your hull, there is a speed that you can reach that is optimal. And then if you want to go faster, then you just have to spend way much more energy to plane the vessel, which is what all these small outboards are doing. But then you end up wasting a lot of energy for that purpose. So it's not optimal. All right, so on board of the ship, we do all of that. We do the ML for identifying what's around it, to compute the navigation, to decide where to go, etc. And this is really what's key, is that there is this capability for the ship to be fully autonomous. If we were to lose a sat link for a week, the ship wouldn't care and would be able to continue with its mission. Finally, Marine AI also built a simulator that allow to build scenarios. Here you see a screenshot that I've taken from one of the from the simulator screen, where you see Mayflower in the middle heading towards the west. You see another ship coming from the top. This is a fake radar target. We have the capability in the simulator to generate radar target. You see it on the right. We generate a radar target that has a certain heading and speed, etc. Which is, and here Mayflower is approaching CPA, which is the closest point of approach. There is a minimum distance that you can approach a ship to based on the size of the ship, its speed, and where you are, if you're on a rail or not, if you're in a channel, in a port, etc. And here this vessel has been intentionally set to cross paths with Mayflower to see how Mayflower reacts. So currently Mayflower has a course over ground of 270, so it's heading west. Speed over ground is 6 knots. And the output of the roll engine on the bottom, which I enlarged to make sure it can be seen properly, is to issue a recommendation to turn 90 degrees to starboard, that is to the right of the ship, so in this case towards the north, and slow down to 4 knots. And because we get in the state which is called a crossing turn, that is, we're going to want to cross behind that ship coming from the north. We don't need to stop and wait until that ship passes in front of us, but we need to slow down and veer towards the right. There's a rule at sea also that every time you start a maneuver, you need to make it so clear that the captain of the other ship can understand what is your intent. So you don't just veer by 10 degrees, you veer frankly to the right and slow down. So in this case, 90 degrees, so you are sure you can actually pass behind this other boat. And the key point obviously here is that because we're using rules, we can trace the decision and we can explain, obviously we maintain a log of all those decisions, and we can explain that in this case, we've recommended to slow down to 4 knots to prevent collision, complying with rule 15 nautical regs. That is quite important. The other thing that's interesting is that we have the second sentence here as part of the explanation. The other vessel should follow a course and speed, which obviously may prove wrong. This is what the other vessel is supposed to do if we follow the international rules and that vessel continues plodding along. But for whatever reason, the captain on the other vessel may decide to change direction, change speed, or may not understand what we're doing and may want to go somewhere else. So this has to be reassessed, obviously, on a frequent basis. We do reassess every second or so. All right, I included a picture here of the 2 most important people in this behavior. On the left-hand side is Don Scott, the CTO of Marine, who was supposed to join us today but couldn't make it. On the right-hand side is Brett Panav, who is the CEO of the Marine company as well, who is basically the one who came up with the vision for this ship and built it, found the funding, funded the company, and hired the right people to make this a reality. Here you see a picture of the ship as it was being dropped in the water. This is one of the previous versions. The ship has been upgraded in the meantime to have more solar panel, but this is during some trials where you see the ship being dropped in the water in Plymouth, UK. And here you see the latest picture of the ship. So a couple of news. The ship actually set sail for the first time in the summer of 2021, sailed for 4 days and then had to turn around. There was a mechanical issue on board. The software worked great, but there was a mechanical issue actually, which has to do with the exhaust piping. Some connector, some steel connector broke. So something that on a usual ship, I mean, the captain goes down with roll of duct tape and, and fixes it in 10 minutes and we're back on the way, right? Obviously here, there was nobody to do that. So the ship had to be turned around back to the CLA island and then towed back to port to fix it. The second attempt was done this year and was actually in April and was actually successful. And the ship managed to cross the Atlantic in 3 weeks. We did suffer a mechanical damage on board, which explained why there was a diversion to the Azores, so that some mechanic could get on board and fix it. Again, some silly component that melted, but nothing with the software. And then the ship was able to cross the Atlantic on its own. If you go to the Mass 400 website, there is a section called Highlights where you will see some videos, including some encounters with dolphin. You'll see the dolphin swimming in the bow of the ship. And it arrived in Nova Scotia in Canada for celebrating the crossing, and then sailed again at sea to Plymouth, Massachusetts, where it is now. And now it's on dry dock in Plymouth with the team over there checking on it and downloading all the data for the science experiment and feeding that data to the scientists. So they have plenty of data to analyze and plan for future expeditions. So that's where we are. I purposely end my show now because we have like 10 minutes left, I think, and I'm sure there will be questions. So I want to make sure we do have some time.
Yes, we do have a couple of questions. Guilhem, that was a fascinating presentation, and I sent the link to the Mass 400 dashboard to everybody on the Slack channel so that they can take a look at it. And then Alan also added the marine traffic for people who are interested in that. It does remind me of the joke about the autonomous factory where all it has is a man and a dog, and the man is there to feed the dog, and the dog is there to make sure the man doesn't touch anything. So, but yeah. I think in your case, the man might have a roll of duct tape so that he could fix that problem and keep you from having to turn back. Jacob had a couple of questions. I'm actually going to ask his second one first because I find that really interesting. Is have you thought about, or do you have a consideration for running multiple interacting Mayflower ships at the same time within the same local limited area? Like, how would they interact with each other?
Yeah, definitely. So in fact, when I mentioned earlier that this is an edge device, there is a reason for that, is that you can think about a fleet of such devices, such ship, that are working in conjunction together so that they can actually go to remote areas where it's hard to conduct scientific experiment or even dangerous areas. You have to understand that if you build an oceanographic vessel from scratch, right, the budget you have to plan for that is north of 150 million, right? Mm-hmm. And you will have a few scientists on board, but they need to handle the weather. They need to fly back to their family. They need to eat. They need to sleep. Right? So the time where they're actually collecting data is not a lot as compared to the time that the ship is at sea. And the ship has to go somewhere, do the experiment, and maybe it takes a week to get back to a port where you can fly the scientists back home and onboard new ones, right? So the efficiency is not great. This can be built at a fraction of the cost of a oceanographic vessel. It can roam the sea 24/7 for 7 months. Right, collecting data night and day. It doesn't care about, if it's cold outside, if I miss my family, I want to fly back home, kind of thing. From the scientist, it doesn't care if it goes to an area where you wouldn't want to fly people or sail people because it's dangerous. So some countries where navigating in those countries is dangerous for your life. So it's so much more efficient. And obviously this is a demonstrator, but it's a demonstrator that worked, right? It's
so if you were to have multiple of these, would they, and they were in the same area, would they talk to each other directly? If they lost the connection with the mothership back home, would they be able to talk to each other via some sort of mesh network?
Yeah, so we haven't built that yet. We thought about building fleets of such vessels to make sure they can roam the seas. Communication at sea between vessels is fairly doable over VHF, right? The VHF is hard because the signal quality is usually bad. People, it's noisy. People, use slang. They speak fast, and it's hard to understand what people say on the VHF. But you could also use data link. There are other data links that you can do with direct site for local coordination of ships. We haven't built it, but it's definitely part of things we're thinking about.
Well, you could go back to Morse code. You could just have a big light on the top of the antenna there, and the camera from the other ship could look at the Morse code. It'd be back to basics.
Yeah, microwaves are used a lot between buildings on sites where the buildings are. use direct light.
Yeah, because I can imagine a group of these who might be on some sort of scientific mission and collecting data, but if they lose connection, you don't want them to be, running into each other or anything. So
definitely.
Yeah. So Jacob's other question was about the optimization engine, asking if it was being executed in real time and what was initiating that, and if it changed optimization objectives on the fly.
So the model is trained on land, and where we have access to how much horsepower we want, right? So finding, and it's the same for the ML model, by the way, it's trained on land. Once the model has been built, it's executed in the ship. So we can, well, the optimization model for the weather, I'm not 100% certain because we have weather data on land. But the ML models and the decision model are definitely executed in the ship. They can run with minimal power consumption. So the key point is how much CPU you need, right?
Mm-hmm.
Unlike vehicles, right, autonomous vehicles, things at sea are not moving that fast. So if you are able to do one evaluation per second, at the scale of a ship, it's a lot, right? Human beings are not even conducting one evaluation of the situation per second when they're sailing.
Mm-hmm.
But for at the scale that we're used to, right, in the IT world, it's very slow.
Mm-hmm. Yes.
We do millisecond execution times usually, right?
Right.
So here we have plenty of time to do the evaluation.
Well, Alan had an interesting question kind of on that same theme about whether this intelligent navigation system could be used as more of a fail-safe form of autopilot on manned ships in addition to the autonomous vehicles like this.
Correct. It is actually part of the intent. So if you go to marinai.co.uk, which is a website of the company manufacturing this, you will see that they also productized it as a protocol Guardian, which exists in a couple of versions. There's a Guardian Autonomous version, which is for this kind of application. But then there's a Guardian Man version, where the intent here is not to steer the ship directly by acting on the robotics, but to give indication to the captain. So it's a second mate on board, basically.
Right. It's like a recommendation engine. Yes.
Exactly. Yeah. You should do this, right? Or pay attention to that, slow down, turn here, whatever.
Well, in lots of business applications, we have recommendation engines that advise a knowledge worker. It's the same concept.
It's like your car when you're starting to be tired and you steer away from the lane. More and more you have those devices in the car where they vibrate your steering wheel or they alarm you to wake you up that you're straying off lane, and you should not do that. And then if you know what you're doing, you get forced. But if you were about to get asleep, at least you have a second chance. So it's the same, right? Wake up the captain and say, hey, did you see this?
So we have time for one last question, and then we're going to have some time for switchover. So Lloyd asked if having this kind of technology as that's demonstrated here, having this become more viable and available, if this is going to have an impact on insurance companies that are covering cargo or delivery. It's like, would you have premiums that get charged differently if you had this kind of technology on a ship?
I think so, because this is what we're also seeing on land. You have more and more insurance company that if you agree, they planted a black box into your car to prove that you're a good driver, will discount your premium accordingly. And I mean, if you look at the news and how many ships are actually running aground per year, containers are lost in storms, etc., there is definitely a need to make navigation at sea much safer. And the insurance company obviously would benefit from that greatly by not having to pay back the cargo of a ship that sank or the damage, the environmental damage of a ship that just ran aground and let go of.
Yes, because somebody wasn't paying attention or whatever, ran into an iceberg or something. Like, think how the Titanic would have been different if they'd had this technology.
Maybe, yes.
Okay, thank you, Guilhem, so much. I know I'm going to be looking at the Mass 400 website and checking things out there, and it was a very interesting presentation. And I think that's it for now. And we have about